All right, so the last video focused on the first intermolecular force of London dispersion, which is, again, present in every covalent molecule, or I'm sorry, between every covalent molecule, and it all relates to the temporary and random motion of electrons, causing all electrons to be on one side of the molecule. That can cause a temporary positive and negative end of a molecule or of an atom. And again, intermolecular forces that are London dispersion forces get larger with more electrons, which is related to a higher mass, as well as more surface area, which is related to a bigger molecule. So this one's going to focus on the remainder of the intermolecular forces. And again, they're not nearly as complex, which is why I can probably fit them all into this one presentation. So force 2 is called dipole-dipole forces. And dipole-dipole forces are only forces that occur between oppositely charged regions of polar molecules. So if you remember when we talked about polarity, we talked about the idea that having polarity means that the electrons are drawn more towards one atom than towards the other atom. They're drawn towards the stronger electronegative atom, and that could relate to or result in a molecule that's polar. And this creates ends of the molecule that are what we call partially positive and partially negative. As you can see in this diagram here, if we have HCl, Cl has a larger electronegativity. So the electrons are going to be drawn towards the Cl more often than the hydrogen. So these two shared electrons are going to spend more time around the chlorine. So we say that chlorine is partially negative. It's not completely negative because that would be a give and take situation where one atom takes the electrons all of the time. That would be an ionic bond. But it's partially negative. That's what the sign at the top means. That's the partial. So most of the time, the electrons are around this chlorine. Some of the time they go back to the hydrogen though. But most of the time they're around the chlorine, creating what we call poles, the negative and the positive ends of the molecule. And what we end up with is negatives and positives in one molecule that can then be attracted to the negative and positive of the other molecule, as you can see here drawn by this dotted line. And this dotted line is usually how we represent those intermolecular forces, showing that they are weaker than the intramolecular force of the bond, okay? And so this intermolecular force occurs between the partially negative and partially positive of another molecule. And that is called a dipole-dipole, between the poles of two molecules that are polar, okay? Dipole-dipole is stronger than LDF because it's more permanent. It's not that the electrons are there all the time, but it's definitely more predictable and more permanent than just due to random motion of electrons. This is a very predictable motion of electrons due to difference in electronegativity. London dispersion forces is due to like the fact that randomly electrons just happen to be in the same place at the same time, causing a partially negative and partially positive part. In this case, this partially negative and partially positive is a little bit longer period of time, and so dipole-dipole forces tend to be stronger than London dispersion forces because they're more predictable, they're more likely due to electronegativity values, and they're more permanent than London dispersion forces are. So what you end up with, if you see this, we have CH3CN down here, and you end up that between these carbons and these nitrogens right here, that's what these are right here, between these carbons and nitrogens, you end up with these attractive forces of dipole-dipoles. You can also end up with repulsive forces, and that causes the molecules to maybe rotate in certain ways so that the positives and negatives actually line up with each other. All right. So again, dipole-dipole is stronger than London dispersion forces, and it's due to the polarity of molecules. So thinking back to when we determined if a molecule was polar or not, one of the reasons that it's super important is to determine if a certain substance would have dipole-dipole forces. Because the stronger your LDF, or the stronger your intermolecular forces, the more likely you are to be a liquid or a solid at room temperature. The more likely you are to have a higher boiling point. The more likely you are to have a higher melting point. The less likely you are to easily turn into a vapor. Because again, the properties of covalent molecules are not determined by the strength of the actual bond, the intramolecular force. The properties of covalent molecules are determined by the strength of the attraction between the molecules. And that's why they have these like lower boiling points and lower melting points compared to ionics. But if I have something that has dipole-dipole and LDFs, because remember, LDFs are present in every molecule, But if I have something that has dipole-dipole forces in addition to LDFs, it's likely to have a higher boiling point or a higher melting point than something that only has London dispersion forces. The third category we're going to talk about is kind of a subgroup of dipole-dipole. It's a specialized dipole-dipole called hydrogen bonding. And again, a hydrogen bonding, not really the best name because it's not a true bond. We usually consider bonds to be intramolecular forces within a molecule, but hydrogen bonding occurs between molecules, okay? And hydrogen bonding only occurs if you have a hydrogen atom that can be attached to an F, an O, or an N of another molecule. I always like to say that hydrogen bonding is FON. And essentially what you have to do is you have to be able to create a FON sandwich with FON on one side as the bread, FON on the other side as the bread, and the hydrogen has to be in the middle. So what you end up having is something that you see here. This is what happens with water, okay? Water is a very polar molecule. The oxygen has the electrons almost 100% of the time. Water is so polar that it's just a smidgen shy of being considered an ionic substance. So because this water, the oxygen has a partially negative charge, the hydrogen has a partially positive charge. The attraction between the hydrogen of one water and the oxygen of another molecule is very, very, very strong. This creates a hydrogen bond, and hydrogen bonds are stronger dipole-dipoles than just regular dipole-dipoles, okay? And notice what I said about that FON sandwich. We've got oxygen on one side of our hydrogen, oxygen on the other side of our hydrogen, and then we've got our hydrogen in the middle. You can kind of think of it like this hydrogen is the one that's just sitting on the bread, and this hydrogen is the one that maybe you put the mustard in the middle so the hydrogen actually sticks to the bread a little bit more. So the strength of attraction between this hydrogen on the right and the oxygen is stronger than the intermolecular force between the two molecules. Because again, intra is stronger than inter. But notice this only occurs with F, O, and N. And one of your pieces of bread could be an F while the other one's an O. One piece could be an N while the other one's an F. It doesn't really matter. They don't have to be the same. Generally, they're the same, but they don't have to be the same as long as it's an F, O, or N acting as the bread of the hydrogen sandwich, okay? The reason F, O, and N are the only ones that can form hydrogen bonds has to do with the fact that those elements have the highest electronegativities on the periodic table. So if you look at our periodic table with electronegativities, you can see that FON is really, really high, and that creates this really strong attraction here because these things right here, these high electronegative elements, they take the electrons almost 100% of the time. So when we say they're partially negative, they're super, super partially negative. Oh, like I would say 99% negative. Whereas in other polar molecules, maybe it's like a 70% negative. In things that are attached to FON to make polar bonds, those are going to be like 99% negative. And so they make those stronger attractions, okay? And again, it's really important that you remember hydrogen bonding doesn't occur just when there's any hydrogen. It's a hydrogen that can be sandwiched between two FONs. And one FON comes from another molecule and one FON is bonded to the hydrogen. That's really important to remember. This is the strongest true intermolecular force. London dispersion, again, very temporary and weak relative to other things. Dipole-dipole, stronger, but not super strong, okay? Hydrogen bonding, really strong. And if you remember back to first semester, we talked about specific heat and that water has a super high specific heat. Because in order to, say, melt water, you have to put a lot of energy in. And that's related to the fact that there's a super strong attraction between these water molecules. So if I want to melt water, if I want to melt ice, I need to break this super strong attraction. So I need to put a lot of energy in. Hydrogen bonding is the reason that water has all the special properties that it has that makes it a special chemical relative to other substances because it has such strong hydrogen bonding, specific heat being only one example. And again, the properties of covalent bonds are not due to the strength of the bond, it's due to the strength of the attraction between the molecules. It's different than in ionic substances. The last category that we're going to talk about, this is called our in-betweener, and it's called an ion-dipole force. In an ion-dipole force, I consider it to be an in-betweener because an ion is not part of a molecule, it's part of an ionic substance, and then dipole is a molecule. So it's kind of like involving a molecule in the dipole part, but also involving an ionic substance. So we're not talking about the strength of attraction between two molecules, we're talking about the strength of attraction between a molecule and an ion. Okay, and this is what happens when you take a polar molecule, such as water, and it attracts to a charged particle of an ionic substance, like an ion. This is how ionic substances dissolve in water. So if you remember when we did ionic substances, we said that they easily dissolve in water because the negative of the oxygen can attract to the positive ion and the positive of the hydrogen can attract to the negative ion. That's because they create what we call ion-dipole forces. And as a result, like you can see in this picture here, you get water particles that surround the ions in a certain orientation, and they basically attract the ion away from its lattice. Okay, and that causes the dissolving of the ionic substances. It's all due to this ion-dipole force. This chart right here kind of helps you determine whether or not certain intermolecular forces are present. There is a document linked to the plan this week that just has this particular chart on it. So maybe you could use it if you want to figure out what forces are present. And remember, London dispersion forces are present between every single molecular compound, every single covalent compound. If I have two covalent compounds, and they might be two of the same kind or two of different kinds, it doesn't matter. If I have two covalent compounds that are in, say, a container together, they will be attracted to each other with those weak London dispersion forces.